Hello, everyone. Welcome to another meeting of our conversational reading group. Today, we are excited to have another great speaker, Fabio Antonacci from Politecnico di Milano. He's talking about AI-based spatial audio. This time, if you have any questions, please keep it for the end of the talk. So drop them in the chat or at the end, raise your hand to ask the question yourself. Without any further ado, the stage is all yours.
Thank you, Pune, for the kind introduction. The topic of this talk will be AI-based spatial audio for, we'll see in a second, the different tasks. This talk is related to the research that has been conducted in the last few years at the Image and Sound Processing Lab at Politecnico di Milano. So first of all, I will start with just a slide related to the motivations for these research directions. So first of all, the first motivation is that the Shannon-Nyquist spatial sampling theorem imposes a number of measurements if we want to obtain a perfect reconstruction of the sound field that is unfeasible in many scenarios. If, of course, we are going to use a standard digital signal processing pipelines. Just a couple of examples. If we would like to reconstruct the sound field in a cube of 1 meter outside, and we want to reconstruct up to a frequency of 1 kilohertz, this basically will imply having more than 300 sampling points, which of course is unfeasible if, of course, we would like to work with rooms of normal sizes. Similarly, if we want to instead acquire a sound field with a spherical microphone array, and we want to adopt a spherical harmonic representation for doing so, at the end we have a number of microphones that scale quadratically with the size of the microphone array and also with the maximum frequency at which we want to obtain our reconstruction. Of course, also in this case, for small to medium sized microphone array working at more than a couple of kilohertz would become unfeasible. Also, and therefore, these basically can be seen as a problem of super resolution. It is also true that there are many inverse problems related to spatial audio that are ill-conditioned. An example of this is the reconstruction of the velocity field of a vibrating surface just from the observation from measurement of the radiated sound field. There exists a linear operator that allows us to predict the sound field from the velocity field, but doing the opposite is very complex. So inverting this operator, the Kirchhoff-Helmholtz integral, is very problematic in many cases. And of course, this can be seen as a regularization problem. So at the end, the basic idea behind this is to adopt machine learning to regularize the problem at hand. What kind of problems are we going to talk about in the next minutes? I have identified 3 of them, which are, let me say, sufficiently complementary one with respect to the other. So the 3 problems are the sound field reconstruction over an extended region. So we have a few microphone arrays in this region, and we would like to obtain the sound field at any other position within this room. And in particular, we are going to see 3 techniques. One is a standard technique with just a minimal adaptation of the standard architectures, and the other 2 instead are, let me say, more popular in the nowadays. The second problem we are going to discuss is near-field acoustic holography. which is exactly the problem of reconstructing the velocity field from the radiated sound field. And in particular, we are going to see a couple of techniques. Both of them basically resort to the class of physics-informed neural networks. And finally, we will have another problem, which is that of upsampling of measurements done using spherical microphone arrays. Okay, let's start then from the first topic, which is sample reconstruction over an extended region. The problem is the one that we have depicted, that I have depicted in this slide. There are a few microphone arrays that have been deployed in a room. So we have local measurements of the sound field, and what we would like to do is to reconstruct the sound field at any other position within the room. In particular, what I'm referring with the sound field in this description. Typically, the most general description that you can obtain is that of the room impulse response or of the room transfer function. Each of these description will basically highlight specific features of the response of the room. In particular, room transfer function allows us to identify the resonances of the enclosure, and it will work, of course, in the frequency domain, whereas instead the room impulse response is in the time domain, and it allows us to identify the direct path, the early reflections, and the later reverberations, and all the features associated to these three parts of the room impulse response. Okay, so what these class of algorithms can be used for? We can use these kind of algorithms for to perform a dataset augmentation. In the case when, as an example, performing some other algorithms related to spatial audio, we need a dense grid of room impulse responses or room transfer functions, or also, as an example, enable scenarios such as walk-through scenarios in a virtual room. So this is called typically as a 6 degrees of freedom. So the user can walk in this virtual environment and, as an example, listen the sound field coming from virtual objects that are immersed in this environment. So the first technique that I'm talking about today is that basically is a standard technique with a minimal adaptation. The observation is that in general, room transfer functions are a complex valued description of the response of a room. And therefore, instead of adapting a standard network architecture for working with the complex values, we directly use complex valued mathematics in this architecture. So what we did basically was to have a few measurements within the room done with omnidirectional microphones and obtain as an output the response at, in this case, more than 1,000 sampling points within this room, starting from a number of measurement points that goes from 5 to 55, depending on the, let me say, complexity of the model shape we aim at reconstructing. As I was saying before, we are using complex valued neural networks for doing this. The architecture is a standard encoder-decoder architecture, and I will directly show some results. On the left column, you have the magnitude and the phase of the ground truth. Then the reconstruction in A for our technique, in B and in C instead the reconstruction obtained with other techniques. The technique in B in particular reconstructs only the magnitude, while in C it's a standard signal processing technique that aims at reconstructing both the magnitude and the phase. To be, let me say, fair, the technique in C is not working in the ideal condition, so the comparison here is not completely fair. However, you can appreciate that working with 15 measurement points, we can obtain a reconstruction of the sound field within this room, which is 4 times 4 times 5 meters, which is quite accurate. What we did basically worked for a maximum frequency of 300 Hertz. In order to go further with the frequency, we should work with a higher number of microphones, of course. But anyway, the advantage is there. This is, as I was saying at the beginning, a standard signal processing technique, neural network architecture that has been minimally adapted for the problem at hand. A different situation instead is for the physically formed neural networks. In general, for any kind of interpolation technique, what we would like to do is to perfectly reconstruct the sound field at the points where the measurements have been are available, and then introduce in the architecture or in the loss function some regularization that allows us to extend the accuracy of the reconstruction to a larger area. So there is a regularization function R that acts on the parameters of the network. However, in for our problem, we also have some prior knowledge that are the acoustic laws. And in particular, we can work either using the wave equation in the time domain, the well-known D'Alembert equation in the first row, or also the Helmholtz equation, basically by considering U, the sound field, to be a sinusoidal function. The solution of the wave equation in general will give us plane waves or spherical waves for two specific boundary conditions, and for more, let me say, general cases, we can resort to equivalent sources to approximate the sound field that we are measuring. We'll say a few more words about equivalent sources, since one of the techniques that I'm going to present is actually an extension of equivalent sources. So what we do then is to devise a network architecture that is typical of the physically formed neural networks, in which the loss function has two components. One is related to the data fidelity term, so basically aims at reconstructing with the maximum accuracy possible the data at where the measurements have been done, and the other component instead measures a loss with respect to the partial differential equation that rules the propagation of the sound waves. Well, the role of the regularizer in this context basically is taken by the partial differential equation. So we don't have strictly the need of having a regularization function in this case. Yeah, here is just a recap of the loss function, which is a sum of the data fidelity, so the mean square error of the reconstruction and the with respect to the measurements. And we have also the component related to the fulfillment of the partial differential equation. There is a lambda parameter that weights the two contributions. So here you have an example of a reconstruction. This is the only example where we don't reconstruct exactly the room impulse response or the room transfer function, but we directly work on a speech signal. So here is a small excerpt of a speech signal, so a bit more than half a second. And on the right, you see basically the waveform of this signal and a zoom in on three different time instants: 1.6, 1.78, and 1.95 seconds. For each of these time instants, it is let me say, a positive side effect, the fact that along with the pressure field, the network can also give us, as an example, an estimation of the velocity, since the particle velocity and the pressure are just related by a differential relationship. So once we have both the particle velocity and the pressure, we can measure the intensity. And in particular, in these three plots, in the insets of these of the waveform, you have the streamlines of the intensity in a volume of 30 by 30 by 30 centimeters. So we can identify, as an example, in the inset at 1.75 seconds, the presence of some singularities within the volume. On the left, instead, you see what happens, what changes if we basically we have available, we have at our disposal a number of measurement points that range from 25 to 75% of the points that we aim at reconstructing. And we also have a comparison with GANs. The blue bars will represent the result of the pin, while the brownish bars will represent the result of the GAN. Finally, we also tested we also worked on the sound field reconstruction using generative models, and in particular diffusion models. So I won't say anything related to diffusion models, because I think it's now popular enough to skip basically the introductory slides for it. I will just say a few words about our use of this model. So as in the case of the complex valued neural network, basically we sample the sound field at some points within the area, and we want to reconstruct the sound field at the remaining points. We also provide to the network as a conditioning information the frequency at which we are working, because of course the complexity of the mode shapes in the room transfer function will largely depend on the frequency at which we are working. And therefore, the frequency is important basically to provide a context to the network. The loss function in this case is just the mean squared error. So you also have an idea of the network that has been used for this purpose in the central illustration in this slide. So as for the setup, we are working with a simulated training dataset of 10,000 rooms, and we have a test dataset of 250 rooms. The room dimensions are random from 20 to 60 square meters. So basically, the room dimensions are random for both in the training dataset and in the testing dataset. So our goal is to demonstrate the generalization capabilities of this approach. The number of available mics goes from 64 to 512. So basically, from 1/16 to 1/2 of the total number of measurement points. Here you have a reconstruction for a variable number of microphones and for a variable frequency. On the top row, you have the ground truth. In the medium row, the reconstructed sound field. And in the bottom row, instead, the, let me say, mask of the available mics. So in general, the technique works quite efficiently. There are anyway some drawbacks. First of all, we are working just in the frequency domain. Sorry, in the magnitude, over the magnitude. So we don't have a reconstruction of the phase. So we cannot directly obtain the room impulse responses from these data, from these results. And we are also not using any prior knowledge about the acoustics. And also, of course, as any other generative approach, we are using much data basically for performing the training. Yeah, this is the last slide as for sample reconstruction. Recently, very recently, we also have presented, but this is a very recent work, not yet accepted, presented a work that instead aims at reconstructing directly the room impulse response. And among all the methods that I presented before, basically this has demonstrated to be, let me say, the best in terms of accuracy. The idea is that we have a federated learning approach. So basically we have a group of networks, each of which is dedicated to perform the sound field reconstruction from a given source position to an area within the room, and then basically by federated learning we can generalize to any possible source position. So please stay tuned because hopefully in a while you will also this other work will be available. The second technique I would like to, the second problem I would like to talk about today is that of near-field acoustic holography, which probably is a bit less, let me say, popular than sound field reconstruction, but it presents some interesting challenges. So what I'm talking about, the idea of the inverse near-field acoustic holography, to be more precise, is that of reconstructing the velocity field on a vibrating surface, starting from the pressure field P that has been measured on a plane that is called as holographic plane that is sufficiently close to the vibrating surface. There is an equation, the Kirchhoff-Helmholtz integral, that basically rules the propagation from the velocity field, to be honest, from the velocity and pressure field on the vibrating surface to the holographic plane. And as you see, it's an integral relationship on which you have the pressure on the vibrating surface, here denoted by Px prime, Py prime, and the velocity on the vibrating surface, here denoted by Vn x prime, y prime. The problem, the inverse problem, basically is that, anyway, of that of inverting the Kirchhoff-Helmholtz integral. So let me say, theoretically, this is very straightforward, but there are some limits. First of all, the vibrating surface will have also some evanescent sound waves that will propagate at the holographic plane very weakly. So these components will be very faint when measured by the on the holographic plane. So basically, if we want to invert and also obtain these evanescent components, if we are able to measure them, these evanescent components will be very weak, so basically the noise will be, they will be affected by noise. So we need a regularization to overcome this limit. The second problem is that of the Nyquist sampling limit that imposes a very large number of microphones. Basically, if we want to obtain a velocity field on the vibrating surface that is above a few tens of hertz, in the most optimistic case 100 hertz, basically above this maximum frequency, the number of measurement points on the holographic plane becomes unfeasible. So we need some sort of a super resolution algorithm to overcome this limit. So for both limits, regularization and super resolution, then we resorted to a neural network-based architecture. In particular, we are using a physics-informed neural network, but anyway, the structure of this neural network is slightly different from the one that we have seen before. The idea is that of course, exploiting the knowledge that is provided by the Kirchhoff-Helmholtz equation and using this knowledge as an external element into the loss function. In particular, we have seen before that the Kirchhoff-Helmholtz equation allows us to predict the pressure on the holographic plane given the pressure field on the vibrating surface and the velocity field on the vibrating surface. So how can we include the Kirchhoff-Helmholtz equation into the picture, into the network? So the idea is that we start from the measurement on the holographic plane, and we, through the neural network, basically we obtain an estimate of the pressure and the velocity on the vibrating surface. And then we use these estimations through the forward propagation, so basically using the Kirchhoff-Helmholtz integral to obtain an estimate of pH, pH hat that you see on the right side of this schema. Of course, everything here is in the frequency domain, and so once again, we are dealing with complex numbers, or complex valued description, and so basically we are using complex valued neural networks to let me say, have a more compact representation of the network. More in detail, the scheme of this neural network is this. We have a single encoder stage and two decoders. One that is in charge of reconstructing PS, so the pressure on the vibrating surface, and one instead that is in charge of reconstructing V. Then through the Kirchhoff-Helmholtz propagator, we estimate pH. And then, of course, I didn't mention this before, but our loss function is based on the comparison between pH at and the measurements pH. We did a preliminary analysis on the best activation functions to be used. Since we are working with complex valued mathematics, we also have to choose an activation function that is in the same at the same time. And among all of them, we have found the cardioid activation function to be the most suitable for our problem. Here we have an example for a vibrating plate. This is a rectangular plate that has been measured on the holographic plane on a grid that is 8 by 8. And in particular, on the left, you see on the column A, the ground truth, both the magnitude and the phase. In the central column, instead, you have what you can obtain with a network very similar to the one that we have seen before, but it works just with real valued mathematics, and of course is adapted to keep into account both the magnitude and the phase. So basically it's twice in terms of in terms of basically of its architecture. On the bottom, on the last two rows, instead, you can see the magnitude and the phase errors. And you can see that in general, the proposed technique achieves a slightly better reconstruction than the real value. Anyway, the difference is not very large, but yeah, I would say that the main achievement obtained by using complex valued networks is the fact that you have a more compact representation of the network. But of course, the number of parameters remains more or less the same. On the right, instead, you see the velocity field that has been estimated on the vibrating surface. So first of all, the velocity field has been estimated on a number of points that is 16 times larger than the number of points on the holographic plane. So this demonstrates the capability of this technique to achieve a super resolution. Yeah, the fact that the complex value network can achieve a slightly better result than the real valued one is confirmed here. Probably more interesting is the fact that the observation that we can draw from this slide. Here you have the Tisne visualization of the bottleneck. Let's focus for the time being on the plot A. Here depicted with the different colors are the basically the elements in the bottleneck related to different boundary conditions. You know that if a plate is working under different boundary conditions, it will exhibit different responses. And in particular, the boundary conditions that we are considered are clamped, simply supported, and free edges. On the illustration in A, the free boundary conditions are represented by these red points here, while the clamped and the simply supported boundary conditions are represented respectively by the green and the blue items in the Tisne visualization. So you can see that different boundary conditions are actually clustered in the bottleneck in different areas. So this is to confirm that the network has also been able not only to learn the one-to-one mapping from the holographic plane to the velocity field, but also some more general description. This is also confirmed by the representation in B, where you don't have only the boundary conditions, but also the different mode numbers for each of the boundary conditions. And as you can see, different mode numbers that are, let me say, related also to the frequency at which a specific mode is observed, are clustered within each cluster in a different region. So basically, the network is not only able to understand the different boundary conditions, but also to understand from the complexity of the mode shapes observed from the holographic plane, the frequency at which this mode shape is actually vibrating. Okay, the second technique related to near-field acousticography is related to a generalization, let me say, of the equivalent source method. In particular, we are talking here about the inverse equivalent source method. A few words about the equivalent source method is a technique that is quite popular in the context of near-field acousticography. What is the basic idea behind everything? Is that of replacing the vibrating surface S with a plane epsilon of equivalent sources. And then to estimate the parameters of these equivalent sources so that we are able to estimate at the best the measurement on the holographic plane. That is what we have at our disposal. And then the velocity field on the vibrating surface is estimated by propagating these optimized set of equivalent sources to the location of the vibrating surface. So this is the, let me say, standard equivalent source method. What we did was to introduce between epsilon and h, so between the planes of the equivalent sources and the holographic plane, a few additional planes that we have called as virtual planes, which basically allow us to better propagate the sound field from the equivalent source to the holographic plane. So basically they will provide us a better way to regularize the equivalent sources. And in particular, what we do is to estimate the propagation from epsilon to the closest virtual plane, and then from one virtual plane to the other up to the holographic plane. So basically, we are adopting a sort of sound field of sparse field discretization. So this is why the technique is called as a physics-informed neural network-driven sparse field discretization. The other feature that we implemented in this technique is that everything is a one-shot self-supervised learning strategy. So basically, we don't need training data sets for this. The network is this. So basically, we have a standard encoder-decoder architecture. And the output of this architecture, which is the V epsilon, so basically the set of equivalent sources on the plane epsilon, is then fed to a few operators from phi1 to from theta 1 to theta 3 that basically will model the propagation from the set of from the plane of the equivalent sources up to the different virtual planes and to the holographic plane. So at the end, the loss function basically is a sum of a data fidelity term between the measurements and the reconstruction of the holographic plane, and also another component that verifies the fulfillment, basically the data fidelity term between the measurements as estimated, the data as estimated from each of the virtual planes and propagated up to the holographic plane, and the data available on the holographic plane. And there is also a regularization term in this network. So here is an example where you see the reconstruction that you can achieve on a violin top plate for two modes, one at 800 Hertz, the other one at a slightly higher frequency, 86 in particular. You have different columns, each of which is related to a different number of virtual planes, going from 0, which is nothing else than the standard equivalent source method, up to 7, which is the maximum number of virtual planes that we have introduced between epsilon and h. So for the first case, that of the mode at 800 Hertz, we can observe that the best accuracy, the best reconstruction is achieved for a number of virtual planes that is equal to 3, Whereas for the other case, the best reconstruction can be obtained for 7 virtual planes. So also the number of virtual planes can be tuned from one frequency to the other. Okay, the last topic is that of upsampling of spatial audio data. So the idea is to virtually increase the number of microphones that have been used to acquire a sound field from a compact microphone array, such as a spherical microphone array. And the idea, of course, since we are using a spherical microphone array, is that of enabling an increased order of the spherical harmonic representation. So just let me say, with an illustration, what we want to do is to go from an array of a reduced number of microphones to a more densely populated array of microphones. Once again, since the acquiring data sets for this kind of problems is very complex and it's a very costly operation, we would like to mitigate the requirement of having at our disposal large data sets for training the network. And also, we would like to include into the network some knowledge about the physics of the problem. An example could be, as an example, the fact that all the capsules, the microphones, are located on a rigid sphere that, of course, has some implications on the sound field captured by the microphones. So this is to say that we have used a physics-informed neural network for doing this task, because both needs can be easily accommodated by pins. So very shortly about the architecture, we have a pin for the real part, a pin for the imaginary part of the or the field that we want to reconstruct, and then both of them are used to, the output of both of them is used to compute the loss function. The loss function is the standard loss function, in which we have a standard loss function of the pins, in which we have a data fidelity component and another component instead that is related to the Helmholtz equation. Notice that in this particular implementation, we haven't kept into account other constraints, other boundary conditions, such as having our microphones on a rigid sphere. One aspect that it is important for this particular, that is, let me say, specific of this architecture is that instead of using the standard sinusoidal activation function that is used in Siren, we have used an activation function, rho-di, that basically has not only a component at the frequency omega 0, but in order to encourage the learning of also higher components at higher frequencies as multiple is the sum of multiple sinusoidal functions. And of course, all these parameters are trainable. So here are some results. And in particular, we have a comparison with a method that is a standard, that uses standard signal processing tools. So no machine learning, that is here denoted as Serita. So on the top row, you have the comparison of the ground truth room impulse response with the one that you can obtain using Sarita and using the proposed method. So you can see that the high frequency components for a specific, let me say, acoustic paths of the room impulse response are better estimated with the proposed technique than rather than with Sarita. This is also confirmed by the plots on the bottom that are the normalized mean square error as a function of the frequency for two particular room impulse responses. And you see that especially at high frequency, the NMSE of the proposed technique is lower than that of Sarita. On the table on the right, this is confirmed over a larger for a larger test data set. And in particular, you have here the reconstruction as a starting from 4, 9, 16, or 25 microphones. Okay, just a final consideration. Some final consideration is related to the fact that working with the spatial audio, we have some requirements, strict requirements in some cases that are related to the phase relationship between the signals that we are reconstructing. Phase relationships if we are working in the frequency domain, or time delays if we are working in the time domain. These constraints can be fulfilled by either conditioning the input, as we have done for complex valued neural networks or diffusion models, or working with a dedicated network architecture that, at their best, can also incorporate into the loss function the partial differential equations that govern the propagation of the sound field. And of course, the network complexity is moderate in the case of physics-informed neural networks, whereas becomes more complex for generative models such as diffusion models. In terms of incorporating some conditioning information into these, let me say, extreme cases, it is easier to incorporate some conditioning into networks such as diffusion models, or also encoder-decoder architectures rather than in pins, while of course incorporating into the loss function the acoustic loss is easier for the pins, while it becomes extremely complex for the case of generative networks. Okay, that's all from my side, and yeah, thank you, and I'm available for any question from you.
Thank you. Thanks for the great talk. So I want to ask the audience, if you have any questions, please drop them in the chat, or you could raise your hand and ask them directly. So there are a couple of questions in the chat. The first question is about, in the sound field reconstruction, are the weight of the neural network complex number, or you have two branches, one for the real and one for the imaginary part?
Yeah, for the complex value, I have a single branch where basically we have a complex valued mathematics. Of course, it is possible to do the very same thing working with the two branches, one for the real part and one for the imaginary part, or one for the magnitude and one for the phase. According to the specific problem, there could be an advantage in using magnitude and phase, or real and imaginary parts. The point is that in some cases, it could be slightly more difficult to let me say, add a constraint about the relationship between the real and imaginary parts, as an example. And so this is why in the reconstruction, I've shown these, sorry, I'm scrolling down and up in the slides. I'm sorry for the for changing so rapidly the slides. This is why in this architecture you have a slightly better reconstruction for the complex valued architecture rather from the real valued one. But anyway, I would like to repeat that the advantage of the complex valued network is just minor, I would say, not basically the same accuracy can be also obtained in the case of real valued networks with the two branches.
Perfect. Another question is, I was wondering if you did an ablation study to see how much does the regularization term that involves the physical prior encoded by the partial differential equation is helping.
Yeah, we did so for the last problem. There was I didn't comment the last slide, one of the last slide extensively. However, everything is here. Um so you see siren and the siren plus PD. So basically, in Siren, the loss function works just with the data fidelity term, while in Siren plus PD, there is a component of the loss function also dedicated to the fulfillment of the PD, or the partial differential equation. Well, you see that in all cases there is an advantage. The advantage is variable from, let me say, case to case. As an example, when going from 9 to 32 microphones, going from a siren to siren plus a PD, we have an advantage of more than 2 dB, 2.3 dBs in particular. While this is reduced for the other, slightly more reduced for the other cases. Similar considerations will apply, of course, also for the other problems where we have adopted pins.
Perfect. Another question is, how well can the RTF-RIR generative model generalize to rooms with different dimension and acoustic properties?
Yeah, that's a very good question. We have tested these basically in just in rooms with different sizes, but with similar reverberation properties. And also with similar aspect ratios. So all rooms were, let me say, with a rectangular floor map or so on. Basically, I would say that the generalization capabilities of this kind of networks to work in a completely different room are limited. Anyway, I would like also to do a step back and give a bit of context for what we are doing. Probably I just I've shown these slides, but didn't comment it enough. So as you see from here, basically we are using these kind of approaches in an European project that is called the Repertorium, that involves several other partners. And the goal here is to enable the basically listen a concert in a music hall from any location independently from where the concert has been actually recorded. This is to say that for the time being, I see these kind of techniques mostly dedicated to a scenario where we learn, basically we apply a training for a specific room, and as soon as we change the room, we perform a new training. We are now working on on an extension that basically performs some fine-tuning on a pre-trained network, but yeah, we are just at very preliminary stages on that.
Perfect. There's one follow-up question, and then I think Mirko has a question. Can you also comment on the fact that when using different RIR generator, although using same acoustic parameter, the generated RRI are very different?
Yes, that's very true, honestly. What we did to basically work with the different RAR generators, also because sometimes we have also worked with the data sets of rears that are synthetic and have been generated using different RAR generators. So what we did was to have, let me say, a pre-processing step that performs some preconditioning on the RIRs so that they are as similar as possible within the training data set. But anyway, this is a very important problem. We are also doing a reality check because on this because we have also acquired, as an example, a couple of the acoustics of a couple of music halls. We are lucky with this European project. We have been able to acquire the acoustics of these halls, and basically in this case, as I mentioned before, we work just with the real data. So everything is done basically just with real data, not using any synthetic data set, and the training is done room by room. So in this case, basically the problem of having RIR generators is completely, let me say, avoided.
I see. Perfect. I think Mirko want to ask a question.
Yep.
Sure. Thank you for the talk, Fabio. Actually, you kind of already replied to my question in part because, my question was about the risk of overfitting of your neural network and the risk that it does not generalize well because, as you said, right, you have to train a neural network for a different room. And so my question was like, if you can create a data set of many different rooms, right, and just fine tune on the specific one. And I'm wondering at this point if you already have some experiments showing that this approach is relevant for your application or not.
Yeah, very good question. Yeah, as I was saying before, we are on the way of developing fine-tuning, so starting from a pre-trained network, also generalizing to new ones. I would say that the behavior mostly depends on the reverberation properties of the room, in the sense that there are some rooms, as an example, what one that we measured was a small music hall in Cremona. You know, Cremona is the birthplace of the violin, and this music hall has been designed purposely for, emphasizing the qualities of the violin. And as a matter of fact, this room, this small auditorium is very dry. So basically has a reverberation time that is below 1.5 seconds. So the sound field in this room is very diffusive. We have tested one of the algorithms that we have seen before in this room, and the result was really horrible. This is the reason for which we have basically resorted to work room by in a scenario of working room by room. Uh, so there is the risk of overfitting. I would say that with the physics-informed neural networks, the risk of overfitting is anyway inherent in the fact that we are using a one-shot approach. So overfitting is what we aim at actually, and not undesired effect.
Yeah, that makes sense. Actually, follow-up question regarding it looks like you are working with real impulse responses, right?
Yeah. In many cases, yes. The result, anyway, just to give you some numbers related to ground truth, were mostly with the synthetic data, the results that I showed before.
Okay, but do
Sorry,
you think like you
interrupted.
can pre-train on synthetic impulse responses and then fine-tune on a real one?
Yeah.
Do you think that's going to be effective?
Yeah, this is what we are doing. As a matter of fact, we have a rear generator that is not the usual Pyroom acoustics or so, but we have a commercial software that is Audion that we have basically we are using for generating sufficiently large data sets. Of course, the estimation of the room impulse response by Audion is way more costly than in Pyroom acoustics, but anyway, this is something that we are doing.
Okay, maybe the very final question, because actually you already addressed this point, but you said that you have some advantage, right, in having this complex neural network, even though it's theoretically possible to have like real value networks and only at the end having real and imagery, really an imagery part. So, but you said that there is an advantage. Like, do you have like a performance advantage? Did you notice something, or where is
Yeah, it's
exactly the advantage?
I would say a side performance advantage. The fact is that when you estimate the real part and the imaginary part separately, it could happen that small differences in both the real and imaginary parts then will have will imply a difference, as an example, in the phase that is way larger than
Hmm.
the difference observed just for the real and imaginary parts. So basically, instead working with the complex valued networks, we are, if not removing this risk is somehow reduced. But anyway, I wouldn't say that complex valued networks will change our paradigm. More or less, similar results could also be obtained in the case of real valued networks.
Perfect. Thank you very much.
Thank you, Mirko.
Perfect. Thank you. I think that we reached the time limit and almost answer all the questions. Thank you again for the great talk. Thank you everyone for joining. Next week, we have Jinyu Lee from Microsoft talking about the development of a spoken language model. Looking forward to meeting you all next week.